this is where we had stopped, right? We had started discussing a little bit about lateral torsional buckling of beams. But just to recap quickly, there were a couple of things that we have discussed. So far, we have discussed only the limit state of yielding, right? And within the limit state of yielding, there were three additional factors that we accounted for. The first one was the difference between my and mp values, right? So the first moment corresponds to the moment of first yield. The second moment corresponds to the plastic moment capacity, right? So these are the first important aspect. The second important aspect was the way to prevent local buckling, because the provisions of this code are applicable only when the local buckling can be prevented, and local buckling can be prevented by maintaining a certain aspect ratio of different elements of a cross section. So for example, if the cross section has a certain width, cross section elements have certain width to thickness ratio, then they can be assessed, or they can be called or classified as slender or compact or something like that, some kind of a cross section like that. And based on which classification that cross section comes into, you will say whether the cross section can utilize its full yield capacity or it cannot. Then the third aspect was the interference with shear, because most of the flexural members are likely to have shear along with bending moment, correct? And because of the shear force that is acting in the cross section, the capacity of the cross section to carry flexure may be compromised, may be diminished. And the design philosophy for accounting for that interference was as follows. I'm just going into a little bit more detail here because there were some questions also last time that were asked. So the methodology for designing for shear, designing for the interference of shear, was as follows. So because we understand that in mostly our thin plate sections, such as I section or box section, we are going to have the web, the vertical element that is going to take care of most of the shear force, right? That we had discussed as shown in this slide. So most of the shear stress is carried by the web as shown here. Correct. So this web will be carrying most of the shear stress, and the flanges will be carrying most of the axial stresses. Okay. However, the web also contributes towards the towards resisting the bending moment in the cross section. Now the question is whether how much is the web contributing towards resisting the bending moment, and the answer to that would be under shear, if the web has yielded completely. Under shear stress, if the web has yielded completely, then it will not contribute at all towards the flexure. So in that case, what you need to do is you just need to take the flanges and ignore the web completely. Just take the two flanges shown here and here, and calculate the moment capacity of the cross section that is made of these two flanges only. Okay, and for that cross section, you calculate MP value or MY value depending on whether the cross section qualifies as a semi-compact section or it qualifies as a plastic or compact section. So if it qualifies as a plastic or compact section, you will take MP values of these two flanges, and from that MP value, you will calculate the capacity. However, if the web has not completely yielded, so then this interpolation formula was given. So if the web stress, shear stress in the web is found to be 60% of the yield stress. So yield stress was Fy by root 3, and the shear stress in the web is 60% of that yield stress. Okay, in that case, you have to start considering the interference between the shear and the moment. And beyond 60%, the interference will lead to a reduction in the moment capacity or the contribution from the web towards flexural resistance. All right. So this plot, this curve here, it's an empirical curve, of course. There is no basis why the formula should be like this. There is no mechanics-based principle that would give you this formula. It's an empirical equation. What it says is that on the horizontal axis, what you see is d divided by bd, which is how much shear is actually acting versus divided by the shear capacity of the cross section, which is basically the shear capacity of the web. Okay, so if the capacity, if the actual shear force is close to the capacity value, that is 1, then you don't take any contribution from the web and you take the moment capacity coming only from the flanges. However, if the shear demand is less than 60%, if shear demand is less than 60% of the shear capacity, in that case, you take the full contribution from the entire cross section. Where does that number 60% come from? Again, I don't have an answer to that. Again, I will. All I can say is that it has been derived experimentally. Okay, so and if it is in between 60% to 100%, then the variation is like this, which is given by this expression here. All right, fine. So I suppose I have answered the questions that were raised last time. If the questions are still there, you let me know. Now I'll wait for 2 minutes. Please let me know if you have any questions.
Sir.
Yeah. Who is this?
For semi-compact section, why didn't we consider shear effects?
For semi-compact sections, why
didn't we consider shear effects? I mean, for compact section, we had a graph.
Yeah.
And for semi-compact section, we only have a formula MdV equal to ZdV, the same formula as without the shear effects.
For semi-compact section, the formula is MdV is equal to Ze, because in a semi-compact section, when you are allowing only the extreme fibers to undergo yielding, right?
Yes.
Under flexure. So basically, let me repeat the question that he's asking. Is it Manthan who is asking this question?
Manoj, sir.
Manoj, sorry. So the question is, it says here that for plastic and compact sections, we have to use this formula, MdV is equal to MD minus beta, MD minus MFD. But for semi-compact section, the formula that we use is MdV is equal to basically same formula that we had used before, Ze Fy by gamma m0. The question is, why is it for semi-compact section? Why is it that for semi-compact sections we are using this formula? Good question. The reason for that would be because the web is not going to yield under flexure for semi-compact sections, because we are not even designing semi-compact sections in such a way so that web would be required to yield. Most of the for the plastic and for compact sections, the way we are designing is we are designing for MP, correct, or substantially higher than My. But for semi-compact section, we are designing anyway for only My. In that case, only the extreme fiber yields. The web is not yielding anyway. So then the interference from the shear should not be that high. Understand? Because the stress in the web because of flexure would be very low. But stresses in the flanges would be significantly high, but then the stress from the shear force in the flanges is very low. So therefore, you can ignore the interference for semi-compact section. All right?
Yes, sir. And one more doubt, sir.
Yeah.
There are other factors mentioned, 1.2 and 1.5.
Yeah.
For simply supported and cantilever.
Yeah.
But in real scenario, we don't have purely simply supported and purely cantilever. What will be the factors for continuous beams?
Yeah, but you have to idealize it for this case. The code does not give you the specific formula for different boundary conditions or intermediate boundary conditions. So you have to idealize. Basically, the fundamental difference between cantilever and simply supported, see, cantilever would be cantilever. You would not have a non-ideal cantilever. If you have a non-ideal cantilever, basically what you have is a failed structure, correct? So let me draw in one sheet quickly. Let me see. So now you can see the blank screen, right?
Yes.
So if you have a cantilever which is loaded like so, now how may you have a non-ideal cantilever? If this support here, if the support is not providing full support, the cantilever would collapse. So there is no way you may have a non-ideal cantilever. For a
but non-ideal simply supported is possible.
Yeah, non-ideal simply supported is possible. But this is an ideal simply supported case. However, you may have a situation where, in addition to being simply supported, it is having some kind of a spring. because usually when you have a support, the support is not really pin support. It is distributed over an area, and you may have some kind of a pin support, some kind of a spring support. So there you may have some moment coming in. So basically the moment diagram that I had plotted, it was like this, but instead it will turn this way because of the presence of the springs. You agree? So a pure simply supported bending moment diagram would be like this. But the bending moment diagram for a beam with some springs would be somewhat like this.
Yes.
Right? So one thing you should notice is that the bending moment diagram shape does not change. And that factor 1.5 was basically driven by the shape. Because if the shape is this kind and maximum bending moment is here, then again a large part of the beam would be under a very significantly high bending moment. Same as in this case. And in this case, anyway, that logic still holds true. That if the bending moment diagram looks like this, then if this is the maximum moment and this is the my value, this is mp, this is my, then only a very small part of the beam is subjected to very high bending moment. Yeah. So that logic still holds true. So in most of these cases, you can idealize a simply supported, even a non-ideal simply supported to simply supported case, and then apply the same formula. Yeah.
Yes.
Okay. Any other questions?
No.
Anybody else? What happened today? Only 13 people have joined. Yesterday, the attendance was much higher. Did people not know that there would be a class today? Or maybe I shared the video, right? So, how was the quality of video? Were you guys able to watch the video again later? Please reply. Did anybody check the video later? Okay. All right. Okay. So this was the interference between the shear force and flexure. Moving forward, now we need to address the issue of instability, right? And we were talking about lateral torsional buckling of a beam. So as I had mentioned, the compression side of a beam. So in a cantilever loaded under gravity loads, you will have the lower part in compression. In a simply supported beam, you would have upper part in compression, as shown here. Okay, and this upper part would have a tendency to buckle under compression, because any part that is in compression would want to buckle. Now there are two ways it can try to buckle. One way would be to move vertically downward or upward. The other way would be to laterally move, right? So if it wants to move vertically, that is in the plane of the major axis, then the challenge is that it has to push the part that is in tension. Plus the beam has a very high stiffness in this direction, in this axis. So moving the entire beam in this axis is hard. Anyway, the load is also being applied in this direction. The beam is deflecting already, but for this buckling element to push the entire beam further, to cause the buckling in this axis, is very difficult. That doesn't happen. What may happen, however, is that this part wants to buckle laterally. Because if it buckles laterally, what you end up with is a horizontal movement. What you end up with is a total net horizontal movement and a net rotation. Sorry. The net rotation of the cross section. So in a sense, what is happening is that there are two major centers in this beam. One center is moving more, which wants to move. The other center, the other point, doesn't want to move as much, but it is being pushed. It is being pulled by the other part to move a little bit, but it is resisting the movement, right? And this kind of a buckling is known as lateral torsional buckling. Why lateral torsional buckling? Because you have lateral deflection, and also you have a torsion, twisting involved. We had watched this video yesterday. I'm not going to show that video again, but you might have noticed that the deformed shape was looking somewhat like this. So at the ends, it is not moving. It is only twisting at the ends, rotating a little. But in the middle part, you can see that there is a lateral movement, and also there is a rotation. Correct? So this movement, sorry, it is marked as phi here, so I'll mark it phi. Okay, so this movement can be classified as two components. One component would be W, the other component would be phi. Phi is the rotation and W is the lateral movement. Okay, and all this is in addition to the flexural deflections because of the moments, the flexural deflections. Okay, this video there are two videos. The links were already given with the slides. You can go through them. Now, the phenomenon lateral torsional buckling has two components, right? Lateral movement, which is a flexural movement. Please give me a minute now. I'll just close my window. There might be some noise coming in. So the lateral torsional buckling has two components: lateral movement, which is a flexural movement, and torsional movement, which is basically torsion, twisting. Right? Now, in order for us to understand flexural movement, we understand very well. We understand what governs flexural movement. Flexural rigidity. Does anybody know what term is called flexural rigidity of a cross section? What is flexural rigidity of a cross section? EI, very good. Yeah, so EI is the flexural rigidity. Now, if we are talking about flexural rigidity in the lateral direction, it will be EI about the minor axis. As simple as that, right? So that is the EI value, and multiplied by EI divided by L or L square or L cube, whatever stiffness term we are looking at. That will be the stiffness that will govern the behavior in the flexural in the lateral direction. Okay. However, when we talk about torsion, it becomes a little bit more complex. Torsion behavior of circular sections you must have studied in your mechanics course, but I suspect that you have not been taught the torsion behavior of open sections, right? Or sections made of thin plates. So the section like an I section, which is most common type of cross section that is used for beams, is an open section. It's a section that is made of thin walls, and it's an open section. So such kind of sections have a very relatively complex torsional behavior, and that torsional behavior is usually split into two parts again, right? So coming back from lateral torsional buckling is made of two components: lateral movement, that is the flexural movement, and torsion. Now, torsion itself is made of two parts. One is called Saint-Venance torsion, and the other one is called warping restraint torsion or warping torsion. Maybe I'll write something here. So we will start from lateral torsional buckling, which is made of flexure in minor axis and then torsion. Okay. Now within torsion, you have Saint-Venance torsion and you have warping restraint torsion. A warping torsion. Okay. Now, I'm not so sure whether you have heard of these two terms, Saint-Venance torsion. Also, it is known as pure torsion. Pure torsion. Okay, and then warping. Warping is actually not a torsion. If you think about it, whatever you understand about torsion is basically twisting of the elements, which is made of shear stresses in a particular fashion. Warping is not really a torsion, but it offers torsional rigidity, overall torsional rigidity to the cross section. That is why warping is classified as one of the torsion types. Okay, so total torsional resistance or torsional moment would be equal to Saint-Venance torsion and warping torsion. Now, what is Saint-Venance torsion and what is warping torsion? We will discuss in the next few slides so that we know where these terms are coming from in the codal provisions. Okay, so what is Saint-Venant's torsion? So Saint-Venant's torsion basically, if I may create another white sheet. So if you have a cross section, let's say I section, and I'm saying that it is undergoing Saint-Venant's torsion. What it basically means is that if you divide this into small cells and look at each cell, independently, what is happening is that each cell wants to twist. So if I draw it in the longitudinal direction also, and I've just separated the cells from each other so that we can understand. So this cell wants to move down, and this cell wants to move up, and it wants to move down here. Okay, so this kind of a twisting is happening in each cell. All right, so this kind of a twisting is happening in each cell, and as a consequence, what is happening is that you are developing some kind of a shear stress between these cells, and that shear stress is often represented, or you may think of this kind of a twisting happening between the fibers, this kind of a shear stress developing between the fibers. So this might be going downward, this might be going upward. Okay, so this kind of a shear stresses are developed, and that is what the torsion is made of. Correct? So that effectively ends up looking like what you can see here. Those stresses end up looking like this. So these are basically shear stresses, which are these what these plots, what you see here in these plots are basically are also known as stress flow. So each flange is twisting in itself. So you can think of each fiber twisting, and when you combine all these fibers to make the flange or to make the web, then each flange is twisting, right? You understand? So basically, if you had a again, I may have to draw it in 2D. So if you have a plate, it may not be very easy to draw it in 3D. When the plate twists, let's say that end, the rear end stays as it is, the front end would rotate. Okay, and then what you are getting is basically this kind of a movement. All right, so this is a twisting movement. So you measure this theta, and with variation in z, how much theta is changing will control how much twisting is happening. So d theta by dz. D theta by dz will tell you the rate of twisting. Okay, so this kind of a twisting of each element is also known as Saint-Venant's component of torsion. The problem with I section, or any section that is made of, or any open section that is made of thin plates, is that Saint-Venant's cannot be the only kind of torsion that is possible. However, if you had, let's say, a circular section, then Saint-Venant's torsion would be the only kind of a torsion. What you would have essentially, are small types of twists. Okay, and they will all cancel out each other nicely, and there won't be any geometric non-compatibility issues here. So it will work perfectly fine, and you would not require any other kind of torsional resistance. However, in members that are made of thin plates, which are open sections, this kind of a problem exists. How? So first we will see how much rigidity do you get for Saint-Venant's torsion. Then we will see what are the issues with Saint-Venant's torsion and why does the other type of torsion exist. So basically, when you talk about twisting of each state individually, so each state is going to be expressed like a action, and the twisting of each state is given by the torsion G, or the new required twisting state is given by G
because for IT, we are familiar with IT. For circular cross sections, we talk about IT, and we use the clear line approach. On the torsion constant, G because the IT will be like some questions.
How is it now? It's just internet based, so I don't know. I don't have much control over the quality of voice. Since how long has it been? Has there been disturbance in voice?
Just now, sir.
Just now. Okay. Is it better now, or is it still?
Yeah, now better, sir.
Much better. Okay. Yeah, I'll repeat. So the Saint-Venance torsion is basically twisting of individual components, individual elements. So Saint-Venance torsion resistance of the entire cross section will be equal to TF1, that is first flange torsion, second flange torsion, and the web torsion. So each one of them have to be twisted, and whatever moment they offer or whatever torque is required to twist them, summation of all these torques will be the torque resisted by the entire cross section. And for each one of them, for the flange or for the web, each one of them, so rather I should write it as integral, it will be G IT d theta by dz. IT, or otherwise what I can say is that IT of the entire cross section is basically summation of 1 by 3 bt cube. So this is a quick expression for thin sections. So if you have a flange which is usually very thin or thin in comparison to its width, so for the condition is that B should be much greater than T. So if it is a flange like this B should be at least 5-6 times greater than the T value. And if that is the case, you can use this expression to define its polar moment of inertia. And G IT, or it's also known as torsion constant, you use IT, G IT d theta by dz, that will give you the torque required to create a unit d theta by dz. All right. So this is how you get the torsional resistance, which you may notice here. Which material property do you need? You need IT, right? Which cross section property? IT, which is given by BTQ. Okay. Now, in addition to that, the challenge with assuming that this is the only type of torsion possible is as follows. Let's say you have a cross section which looks like this, I section, okay, and now let's say both flanges are twisting. So at one location, let's say where the support is, where there is no rotation, the cross section remains as it is. But where there is decent rotation, you would have a cross section where the flanges would twist like this, and the web will also twist like this. So web is twisting about its center, the flanges are twisting about their own centers. Now, if you compile all the three together, you will see that the web has deformed to this location, and the flanges have deformed to this and this configuration. What is the problem here? The web will not be connecting to the flanges where they were connecting before. That means the web has to be, there is a displacement compatibility problems. There is compatibility issue here because the web has to be detached from the flange and rotate independently. But that is not how the cross section behaves. The cross section behaves as if the web still remains connected to the flange at the same location where it was connected. So that clearly means that if we consider Saint-Venance torsion as the only type of torsion resistance, then this kind of a compatibility issues will arise. Okay. How do we address this? Basically, what has to be done is that now the flange has stayed in its position, but the web has moved. Now, for the web to be able to move, the flange has to be moved along with the web. So if the web has to twist this way, the flange cannot stay in its original position. Okay. The flange stays in its original position, the flange stays in its original position, the web stays in its original position. Only twisting will create this lack of compatibility. So what has to happen now is that for the web to twist, the flange cannot stay in its original position. That means the centroid of the flange cannot stay in its original position. The centroid of the flange has to move this way. And the centroid of the flange here has to move this way. Similarly, the web also cannot twist as much. It will be twisting less. Okay. What does that mean? It means that the flanges have to undergo lateral movement in opposite directions to maintain the compatibility. And that is where the warping comes into picture. Okay. Now, please follow me here. Please follow this argument very carefully. This is very important to understand what warping is. So let's say you have a beam. This is the beam. In this beam, you have a top flange, you have a bottom flange, and you are looking from the top. Okay, you are looking from the top. So where the support is, at this location where the support is, all you can see is the top flange, because the rest of the beam is hidden behind you. Okay, and now you apply a torsion on this beam at the free end. So you apply a torque. What is the name? You apply a torque on this beam at the free end. So as you apply the torque, the web would twist. And as the web twists, it forces the flanges to move. So the top flange moves in this direction and the bottom flange moves in this direction. And the top flange moves in this direction. The top flange moves in this direction and the bottom flange moves in this direction. Okay? Now you follow? That movement of individual flanges is not really a twisting. What is it? The top flange was initially a straight plate. Now it has bent. Correct? It has to bend. And that is purely a bending problem of individual flanges. So the two flanges are bending independently in opposite directions. Okay? And that is governed by the twisting of the web. Now, when you know that it is a bending problem, we know how the bending behavior of each flange is. So bending would basically require that the flange undergoes some part of the flange, half of that flange undergoes tension and half of that flange undergoes compression. Similarly, for the bottom flange, half of it goes under tension, half of it goes under compression, and we know the flexural behavior. Along with that, there will be some shear force because the web would require the flange to push. So web would be pushing the flange one way, and that will lead to some shear force transfer to the flange. Okay, and if we take that shear force BF, multiply with this interval gap between the two flanges, that is HF. So VF multiplied by HF gives you that warping moment. What is happening essentially is that top flange is being pushed one way, and the bottom flange is being pushed one way in a different way, right? So the top flange is probably being, let's say, so if you look here, the top flange is being moved this way and the bottom flange is being moved this way. So there is a force BF applied to the bottom flange, same force BF is applied to the top flange. And the distance between the two flanges multiplied by VF will give you additional torsional moment. Okay, but if you look closely, it is actually made of two flexures of two different plates, but it essentially turns out for the entire cross section as a torsional moment. VF multiplied by, so this VF is acting in this direction. Maybe I'll put another color. Can I pick another color? Yeah. So this VF is in this direction, and this VF is in this direction. VF multiplied by HF will give you the torsion, warping torsion. Right? All right. So warping torsion is given by that, and then you can derive it further, which depends further on the cross-section property. One cross-section property that is called CW, often referred to as IW. So IW and CW are basically the same, are referring to the same term, which is called warping torsional rigidity. Now here what you may notice is that the warping torsion value is proportional to not d theta by dz torsion, sentinance torsion. In case of warping torsion, it is proportional to d3 theta divided by dz3. That is third derivative of theta. Okay. For I sections, the value of CW has been calculated, which turns out to be thickness of flanges BF cube, width of flanges cube divided h square by 24. H is the distance between the two flanges. Okay. There is a little bit of mechanics involved. I am not deriving these expressions here individually, but if you are interested, you can refer to any standard mechanics book and you will get the expressions. It will be derived for you there. Okay. So, any questions about warping torsion and Saint-Venance torsion so far? Any questions? Were you able to follow what I was saying?
Sir,
Yeah.
sir, can you explain how the shear forces develop in the flanges?
Charu. Okay. How the shear forces develop in the flanges? In case of Saint-Venance torsion or in case of warping torsion?
Saint-Venance. Saint-Venance.
Okay. In this one, right?
Yeah.
Okay. Okay, I have to create a screen here. 1 second. So we had shown this flange, right, which is made of individual fibers, if you can imagine. All right, so each fiber, what you can imagine is that each fiber is twisting independently. Okay, so if each fiber is twisting, this fiber wants to go downward, this edge of this fiber wants to go downward, and this edge of this fiber wants to go upward. Okay, and then this fiber of this, this edge of this fiber wants to go upward, and this edge wants to go downward. Similarly, this wants to go upward, this wants to go downward. Now what will happen is that this and this shear stresses will, and similarly here also, this is what the twisting would be, right? I'm sorry, pen is not working very well. All right, so now what will happen is that this shear and this shear will cancel each other out. Similarly, this shear and this shear will cancel each other out, and so on. What you will end up with, similarly, this shear and this shear will cancel each other out. What you will end up with is you have a plate, and imagine that you have a neutral axis in that plate. That is the same neutral axis drawn here. So these fibers will be pulling this way, pulling this way. These fibers will be pulling a little less. This fiber will be pulling a little less, and these fibers will be pulling this way, and this way. Okay. So if you remember from your circular section torsion behavior, how was the shear stress distribution? Like so, right? Can somebody confirm? Oh, every time I move out of the slide, I lose that. Sorry. I should have this slide. So, as I was showing, what happens is that if you imagine that this is one cross section in that plate, and then there is another cross section right next to it. What is happening is that one cross section is the cross section that is outside of the plane of this screen is pulling this cross section that is shown here in this direction, and the cross section that is outside is being pulled in the opposite direction. So there is this kind of a shear stress acting, and this shear stress is maximum right next to the edge, and it's smaller near the almost zero at the centroid. Yeah. So at the centroid, it's small. As we move away from the centroid, it is larger. Similarly here, it is larger, and this is the shear stress that is being applied by the subsequent cross section. So one cross section is applying this kind of a shear stress on this cross section. Similar thing happens in a circular section. So you have this kind of a shear stresses. Which plane is applying that shear stress on this plane? The plane that is outside of the plane of my screen, right? So there are two planes that are matching each other. One plane, if you can see here, my hands, watch my hands. So if you have one plane, the other plane, and the other plane wants to move with respect to this plane. Okay, so the points that are farther away from the centroid are moving more with respect to each other, and therefore they have higher stress. Similar thing happens here. So these are the shear stresses that would be developed. As a consequence of these shear stresses, you will end up getting a twisting in the plate. Yeah, so the plate was going this way. If let's say that end is fixed, you will end up getting some kind of a twisting. So the twisting will require, if this is the neutral axis, the twisting will make it go up this way and this way. Okay. Understood? Is that clearer? Guys, please reply. Or any other questions? Okay. So if it was a single plate, it can still undergo almost pure torsional, pure Saint-Venant torsion without having to indulge into, or without having to involve much warping. There will always be some little bit of warping. If the cross section is not perfectly circular, there will be a little bit of warping always. But if it was single thin plate, the warping moment will be very small and you can ignore it, and it will be purely Saint-Venant torsion. However, when the cross section is made of three plates, like shown here, so either it can be a channel section, it can be an I section, it can be a box section, no matter which kind of. And the reason for that is because the joint between the plates creates lack of compatibility if there is no warping. So as a consequence, you get some warping. Warping is basically nothing but the bending of two flanges in opposite direction. Okay, and you can derive the expression for that bending moment or the shear force required to create that bending, and that shear force multiplied by the gap between the two plates will give you the torsional moment. Yeah. So this torsional moment equation is given as here. So basically, the total torsional moment that is required to twist an I section will be a summation of TW and TSV, as I mentioned here. Total T will be equal to TSV plus TW. Okay, so that is the torsional behavior. Now, so far we have seen certain cross-section properties which have played a role. One is IT of the cross-section, which is basically summation of 1/3 BT cube, shown here. Right? The other cross-section property that we have seen playing a role is IW or CW, right? That controls the torsional behavior. One more property that we had discussed in the beginning was flexural in minor axis. So this one was EIY, right, in the minor axis direction. So these three material properties, cross-section properties, you would see playing some role. So there should be a G. If you see in the expression, if you see a G, that obviously means that GIT is playing a role, because there is no other place where G is used. Correct? That means Saint-Venant torsion is playing a role. If you see any use of E multiplied by CW, then obviously warping is playing a role. Okay? And if you see any IY mentioned, that means flexural bending or flexure in minor axis is playing a role. So this is the expression that is given in our code for elastic buckling of a lateral torsional elastic buckling of a beam, and this is coming for purely elastic cases from eigenvalue analysis. So it is exactly equivalent of your P critical is equal to pi square EI by L square that you are so well familiar with. Okay, so you got this one from eigenvalue analysis. You can do similar kind of eigenvalue analysis, just a little bit more involved, and you will get an M critical value, which will be having terms of EIY. What does that mean? EIY corresponds to flexure in the minor axis, in the weak axis. That is your lateral part of the lateral torsional buckling. Okay. GIT corresponds to St. Venant's torsion. W, if you see the value of W, which is to be taken from here, it has expressions of IW and GIT, right? So EIW is basically your warping resistance, warping torsional, fine, and that is your W. So you substitute this W into this expression, and you will get the overall expression. Where does it say in the code? You go to clause number 8.2.2. Here 8.2.2.1. Okay. Elastic lateral torsional buckling moment. So this one is under pure elastic cases. It is not a realistic case. It is not really applicable directly to any beam. It is derived only for the elastic beams, and elastic buckling is very unlikely. Usually what you would have is inelastic buckling. There will be some yielding in association with some buckling. Okay, so the expression is given here. That is exactly same expression that is given here. M critical is equal to pi by L EI by GT. You just need to rearrange some terms. You will get that expression. Okay, all right. Any questions? No? All right. So I think I have written it incorrectly here. This is not for doubly symmetric cross section. I think it is applicable to all cross sections, even for not for doubly symmetric. I'll have to recheck this once. Because here it says in case of simply supported prismatic members with symmetric cross section. I don't know whether it means symmetric or doubly symmetric. I'll recheck and get back on this one. Elastic lateral buckling moment or lateral torsional buckling moment can be determined as this expression. Okay. Now, further in this same code, it says that it can be approximately calculated from the values given in table 14, which have been prepared using the following equation. So they have basically, right now you are required to, in this expression, you are required to calculate IW value and IT value, which might have been involved. IT is still easy. IW depends on different cross sections, but here they have already solved for various values, and all you need is the HF, TF. So HF is the spacing between the flanges, TF is the thickness of the flange, RY, right here. So HF is the spacing between the gap, the distance between the two flanges. RY, you are familiar with. TF, thickness of the flange. LLT is the length of the beam, unsupported length of the beam. I'll talk about LLT in a minute. Okay, and then they have further simplified that equation for symmetric I sections, rolled I sections and doubly symmetric I sections. So if the cross section is doubly symmetric I section, then you can use this expression. So this is further simplification of that expression, and the values of M critical are also given in table 14. Now you must remember, it's very critical, it's very important for you to remember that this M critical value that is given here is only for elastic buckling case. So all these three expressions that are given here, F critical or M critical, they are all applicable to only elastic buckling case, which is not a real buckling case. What happens here is that, just like you may remember, when you were calculating the column capacity, you had to first calculate P critical or PE. You remember? You had to calculate PE, right? And PY. And then PE and PY, you had to interpolate between them, and there was a factor chi, like so. This kind of a factor was there, and that factor was used to do the interpolation between P critical, PE and PY. Similarly, we will calculate M critical from buckling point of view, and we will calculate, we already have calculated MP or MY, depending on which case it belongs to. So then we will do an interpolation between these two to get the actual equation. Okay, so what does the equation look like? Design equation looks like NB is equal to beta B. Beta B is just making sure that you are using MP or MY depending on the requirement. Beta B ZP. Okay, so this basically means MY or MP, as the case may be. If it is semi-compact, you will use MY. If it is plastic or compact, you will use MP. Chi factor is the reduction factor, and Fy gamma m0. The chi factor is basically doing the interpolation for you, wherein you use phi. Phi depends on lambda LT. Lambda LT depends on your ZPFY, which is MP and M critical. So that's where your M critical goes into. Your M critical goes into calculation of lambda. Your lambda goes into calculation of phi, and your phi and lambda again go into calculation of chi. That you substitute here. Okay. And then in between there is a factor alpha that you have to use. That factor alpha is basically imperfection factor. Just like you had 4 different imperfection factors for columns, you have 2 different imperfection factors for beams. One for rolled section, the other one for welded section. So what we can do now is, I think we are running out of time. Yeah, it's almost the time. Okay, so I'll stop here now. If anybody has any questions, you can ask now. You can unmute your mic or you can type the question. So we have just discussed the design equation, and we will see how the different equations compare in the next class. Yeah, ask the question, please.
Sir, in the beginning, you said that there is a difference in the formula for semi-compact and compact. Can you explain why?
Let me go back slide-wise. You tell me on which slide are we talking about?
Here, sir.
Here.
Yes, sir.
This question Manoj had asked, right?
The same thing what Manoj asked.
Okay. So, see, what is this formula trying to do here? It is saying, the formula is saying, is that web, if it is going to undergo some yielding or some very high level of stresses because of shear, then it will start interfering with the moment capacity, and you may not be able to use full moment capacity. That's what this formula is saying, right? This formula. Agreed?
Yes, sir.
Okay. So now, in case of semi-compact section, you may have large shear, but in semi-compact section, what is the design philosophy? The design philosophy is that the flange, extreme ends of the flange are going to be at Fy value maximum. At that time, the web, most of the web, maybe the extreme parts of the web will also have some stress, but most of the web will be at a very low stress level, because you are not designing the section for complete plasticization in flexure. So when you're designing the section for flexure, the web is at a very low stress level, because only the extreme fiber is going to sigma y or Fy, which is in the flange, and the middle part where the web is at a very low stress level. Okay. So at that stress level, you can simply assume that the shear is not interfering now, because the web, the stresses because of flexure in the web are very low, and the stresses in the web because of shear may be high, but they will anyway will not affect the overall moment capacity of the cross section very much. That is what it means here. Is that, does that make sense?
Yes, sir.
Yeah. Anybody else? All right. So I think I'll stop here now. I think I have exceeded the time for today. We will continue again. When is the next class? Monday, right? I think so. Anyway, we will have the classes on the regular schedule whenever it is scheduled as per the calendar, as per the timetable. We will have it at that time. Okay. All right. Thank you.